Welcome to the 2017 MOSRP Executive Summary, where we'll describe our program's objectives, projects within the program, goals and deliverables within those projects, progress in each of those projects, plans, and new opportunities. The outline of the talk is we're going to describe how we define and address outstanding and prioritized seismic EMP challenges. We're going to provide a single and accessible comprehensive framework that allows all of the methods that this group pioneers, develops, and delivers to be derived from one simple single starting point, providing an understanding that could help for some of our approaches which are for some people inaccessible. The goal is to make them as accessible as possible. Then we'll go through the projects, their objectives, progress, deliverables, and plans, describe a new opportunity from MOSRP, and lastly, a summary in the road ahead. So MOSRP identifies and addresses outstanding and prioritized seismic exploration challenges. Challenges whose solution would have the biggest positive impact on our ability to locate and produce hydrocarbons. So a real question is, how do you decide on what the problems are, what the challenges are? And we'll have quite a bit to say about that within the next few minutes. This presentation today is, as I mentioned, an executive summary of our activity, which is a sampling. There's a link nearby which provides all of the presentations from our recent annual meeting, technical review. And in addition, there is another link that has all the slides of this presentation. So if we're going too fast at some point and you want to focus in on a slide or another, there's another link that you can just stay with any slide you want to see in more detail, okay, if we're going too fast. So why are there challenges? Every seismic method, without exception, including, of course, everything that this group develops and produces, are based on assumptions. They have prerequisites, they have requirements. When those assumptions, prerequisites, and requirements are satisfied, the method is effective. When they're not, the method will have issues, can fail, and that can be one of the causes of dry hole drilling or suboptimal development drilling, that failure. What are the types of assumptions, the categories of assumptions? We could list as one assumption is that you've acquired the necessary data for that algorithm to be effective. We'll have quite a bit to say about that as well. You need to have adequate compute power so that the turnaround produces a result in a timely fashion so that you can use it. And last but not least, our innate algorithmic assumptions and requirements. What in the derivation themselves of the method have you assumed? And are those assumptions and requirements and prerequisites being satisfied? So how to address an assumption that's not satisfied? If the assumption is not satisfied, it leads to a challenge. We view the response to that in two different ways. One is, if a method has a requirement, one way to, and it's not being satisfied, find a way to satisfy it. Find a new method that more effectively can provide the prerequisite, an assumption, than is currently available, because the current available method is not matching the required satisfaction. Another approach to an assumption that is not being satisfied is to find a method that doesn't have the assumption at all, doesn't have that requirement. So, so those are two different attitudes that we adopt for different issues, and for either one or the other is called for from our point of view under different circumstances. So examples of where we try to satisfy requirements. Many methods require deghosting. Deghosting is important for bandwidth, for notch removal, for all inverse scattering series imaging and multiple removal, all imaging that's not inverse scattering. Conventional imaging that requires a velocity benefits from deghosting. Wavelet estimation. Methods that require the wavelet, we find ways to provide the wavelet. The same with deghosting. More effective methods than are currently available to match a need that where the deghosting methods currently available sometimes will satisfy the need and sometimes they won't. When won't they? And find a way to add to the toolbox so that circumstances which are currently not able to be addressed are addressable. Ground roll removal without damaging reflection data. That's something you'll see how we pursue that. That's something, ground roll removal is required in order to process reflection data. We don't know a way to avoid that. We have to find a way to do that effectively, okay, to satisfy that need. And then direct inverse for velocity estimation. There are migration methods that require a velocity. We believe you should look at direct inverse methods, parameter estimation methods, to determine the velocity. And we have pursued that type of activity. Now, to understand assumptions, it's useful to take a look at the evolution of migration and multiple removal. How did migration methods evolve? How did multiple removal methods evolve? And what's the relationship between that evolution and assumptions they made or requirements they had? So if you look very briefly at migration, there was a time when it was post-stack data and time migrated, then post-stack depth migrated, then pre-stack time, then pre-stack depth, then RTM. In each step of this evolution, the migration method became more effective. It had more physics incorporated. It had, however, as it became more effective, at every step in that evolution, it had a commensurate higher need for accurate velocity. And if at any point the need for the next capability could not be satisfied, people backed up, took a less effective migration that had a less demanding velocity, rather than a more effective that they couldn't satisfy the velocity. So that's one set of assumptions. You see an evolution of assumptions within the area of migration. Multiple removal, the same. Predictive decon, stacking, FK filter, radon, model and subtract, SRME plus feedback loop for internal multiple from Delphi. In each case, as these methods became more effective, there was again a commensurate need for more subsurface information. The issue is when the industry trend went to deep water and more complex plays, often the demands of those methods for more detailed subsurface information was not able to be satisfied. And that remains the case today. The issue of finding an accurate velocity adequate for the more sophisticated migration methods is far from a closed subject. Far from a closed subject. That's a inconvenient statement to make, but the best methods we have today are partial solutions. Okay? Partial solutions to that problem. It remains an open issue. So there is a set of procedures, the inverse scattering series, task-specific subseries, the last bullet here, that says that, and you'll see the logic behind that statement, the inverse scattering series says that every processing goal, task, objective that you can imagine is directly achievable in terms of your data and without subsurface information. Every task that you can imagine. Free surface multiple removal, internal multiple removal, depth imaging, nonlinear amplitude analysis, Q compensation without Q. Okay? No Q information. In comes the data, experiencing Q, out comes the data as though it never had Q, yes, without any information about absorptive dispersive subsurface. So that inverse scattering whole approach is a package of concepts, of potential, of ideas that are designed exactly to deal with the inability to provide accurate information, subsurface information that many algorithms require. So we're interested in a consistent and aligned set of processes. We look at the entire processing chain. We don't take something downstream and assume all the upstream requirements are satisfied. Well, if this and that was satisfied, then what we're doing would work. No, if it needs things upstream, it's our responsibility here to provide them. Okay? The entire seismic processing chain is this group's responsibility. That's the chain. It starts on top, where and this is the marine case, where the reference wave is separated from reflection data, reference wave being the part of the data, the events that you have recorded that have not touched the earth. Reflection data is data that's reflected from the earth. Then the reflection data is separated into ghosts and reflection data without ghosts. Once the ghosts are gone, the reflection data that's deghosted is separated into free surface multiples and primaries and internal multiples. Then primaries and internal multiples are separated into primaries and internal multiples, first by reducing and then eliminating those internal multiples. And then there's a set of activity here for migration and amplitude analysis that input primaries. Okay? So the green dots right now, just remember those are derived from Green's theorem, and the yellow dots from the inverse scattering series. We'll get back to that as we go through this processing chain. This presentation follows the chain, as the projects that we will describe will take us through the chain. Okay? So what we put data through is what we're going to put you through in this talk. So there are words for that are used for seismic processing methods. Modeling. Modeling, we understand you have some model of the subsurface. You settle on a model type, acoustic, elastic, anelastic. Within the model type, you describe the configuration of properties, interfaces, and so on. You define a source, and you generate, numerically generate a wave field that is excited by the source that you've assumed and that has experienced that subsurface, and then is so you produce the field numerically inside that medium and outside. And so you can collect synthetic data outside this medium that you assume you've modeled, and the data represents what that source would produce in that model. Yes, that's modeling. Inversion is the inverse of modeling. Inversion is you give me a source, you give me some medium that you don't know that's being interrogated, you assume some wave has entered this medium, and then this wave eventually returns, parts of it return to a measurement surface, and recordings of the wave on that measurement surface are then to be used to determine what medium that wave has experienced. Okay, determine it. And there are two ways that people look at this. One is what we call direct, and one is indirect. So before we get into too much more about direct, indirect, let me give you some example. Here's a formula, very famous formula, very old. Everyone's learned this in elementary algebra. you have an equation ax squared plus bx plus c is 0, and right below it you have the solution. Someone gives you a, b, c. On one side is a formula that takes in a, b, c and outputs the two values of x. That will satisfy that equation. That's a direct solution. Okay? An indirect solution to that problem would be try to find a value x or values x that make ax squared plus bx plus c squared a minimum, or some other power, yes? Some property that you assume is associated with being 0, be small, yes? So let's stay with this simple example for a minute. Humor me and assume for the moment that this equation, ax squared plus bx plus c is 0, was relevant to seismic exploration. That solving that equation will lead to drill decisions. Drill here. This x, these are the values of x that you should drill, yes? And let's say that you had that equation, which you, for some reason, we're going to assume is relevant. That's the equation of interest that we've decided is relevant for making drill decisions. And you have this direct solution. And then you make drill decisions based on that direct solution, and you don't improve your drill success rate. You don't improve your drill success rate. Then you know that ax squared plus bx plus c is 0 is not the equation you should be interested in. Why? Because if that's the equation that you're interested in, there is no doubt that that is the direct solution. There's not a question that you could find another solution. That is the solution. So if it's not working, you can't blame the method. You know that the problem that you're interested in is not the problem you need to be interested in. That is so important, because problem definition is the key to solving problems. What are the problems? If you have an indirect solution like this, and it leads to unfortunate drill decisions or not improved drill decisions, well, let's try cube. Let's try fourth. Let's try 3/2. Let's try weighted sums, you know? And then you have workshops on it, okay? And special sections of journals on that indirect, because everyone's going to have their view of that. And the problem is, the real problem is, if you think if you think ax squared plus bx plus c is 0, is relevant, is the problem of interest that you should be interested in, and you do this and it doesn't improve your drill success rate, you don't know what the reason is. You don't know whether the problem of interest is not the problem you need to be interested in, or it is the problem, but you didn't find the right indirect solution, so you keep searching for different global searching and so on. So direct solutions, when they're available, are extremely valuable, because if a direct solution to a problem that you decide is of interest doesn't lead to an improved drill success rate, you're solving the wrong problem. That's simple. You don't have to search. You directly solve that problem. The signal back is you need to be solving a different problem, okay? And that's invaluable, okay? So with that, what we just said is what's on this slide. Indicators of indirect, model matching, objective cost functions, search algorithms, iterative linear inversion, you'll see more about that, necessary and not sufficient conditions, like common image gather flatness. These, if you see these words in a method, it's indirect. Is indirect evil? No, it's indirect. So it's something very important, because we've had some direct statements about certain methods. The methods that we have made comment on are not the problem. The problem is the people who use them and oversell them. The method is just a method, it's a tool. It's some math that leads, and it will have a place. The problem is when people take any method and say it's the final and ultimate solution. Then what happens is we criticize the method. It's not the method. Okay? The method has a place. It's people overselling it that causes an issue. Okay? Why is overselling a problem? Because at some there'll be some initial rush. Yes, we have the final and ultimate solution. Then there'll be disappointment. Okay, eventually. Okay, because no scientific method can be the final and ultimate solution. Okay, so that disappointment can give research overall a bad name, and shut down research labs or shut down research groups. Just none of this is worth it. Okay, and that's the danger. Okay, so in our view, there's a role for direct and indirect. If you can write the physics, an equation down, then you should look for a direct solution for the reason an equation that you think is adequate or appropriate for your purpose. No matter what equation you write down, I don't care what group it comes from or what company it comes from, every equation that we ever write down is an approximation. Well, you got an exact solution. No, you have an exact solution to the equation you wrote. The equation that you wrote to begin with is approximate. Okay? The Earth is more complicated than the equation that we write. And we need to accommodate, we need to understand, respect, and respond to that difference between our physics and what the Earth is. That's where we believe indirect resides. You have to have a channel for what's outside of your assumed physics. And so looking for a criteria, hopefully that will align with the direct method, an indirect criteria for the part of the universe that's outside your physics is what we feel is the appropriate place. If you ignore that, that's at your peril. Okay? So we believe you need a very effective indirect method to deal with the parts of your measurements that are outside of your physics. Okay? So we'll have some more to say about that. So here's this unifying framework that we promised. In other words, we're going to provide a framework that's unusual to many people, maybe some people here as well, that gives a way to understand all these diverse methods we work on here. Deghosting, ground roll removal, free surface multiple removal, depth imaging with a velocity, depth imaging without a velocity, all coming from one starting point. Okay? All of that from one starting point. And so that will provide what I just said, that comprehensive framework will provide for wave field separation methods like deghosting and ground roll removal, wave field prediction inside a volume where you assume you know the medium for that kind of migration, and all of the inverse scattering methods and what they provide. One single starting point predicts all of this, produces all of that. That's useful. That's useful conceptually, and in particular for many of the concepts here that seem counterintuitive. So we're going to start as follows. Here's a homogeneous acoustic world. Imagine this. And then imagine that in this world there's a point source, a Dirac delta point source at R prime, and you're looking at the field at point R. There's a whole homogeneous universe with one point source, and here's the field. And in addition, we're assuming that point source is vibrating at one frequency. Okay? In other words, it's not delta in time. It's been Fourier transformed in time to omega. and it produces that equation 1 there. And that G0 plus indicates it's causal. In other words, there's a wave that only exists after the source goes off and moves away from the source. Okay, the causal solution to that problem. And K is omega over C0, where omega is that temporal frequency I alluded to, and C0 is the velocity of this infinite whole space. Okay? We're going to go from this to every single thing on that chart. Okay? From this simple, so why? Because the development will have a common starting point and then a logic. So if some of the conclusions, like Q compensation without Q, are troubling, I invite you to look at the starting point and the steps between to find the flaw. Yes? If there isn't, I further invite you to examine your preconceived notions, yes? And to open to possibilities which are currently non-orthodox or conventional, yes? So now imagine that instead of one point source at R prime, there are 3 point sources. One at R1 prime, R2 prime, R3 prime, with weights A1, A2, and A3 at those 3 points. In other words, each of those Dirac deltas has a weight associated with it. And then the solution P for so you still have a homogeneous whole space acoustic with 3 point sources, and you're looking at the field at R. These are the sources at these different locations. This is just summing them up, so you see the weights times the source at a given position R sub I prime. And then the solution, because del squared plus k squared is linear, yes, the solution for P, due to this source plus that source happening simultaneously, is the solution to this source alone plus this source alone plus this source alone. This. Okay? That comes from the linear nature of del squared plus k squared. And so you have this general form here where you have some discrete number of point sources in this homogeneous a whole space where this is the field due to those discrete point sources at some position R. We're going to move from this, where they're discrete, to continuous, a continuous distribution of sources. So if the distribution is rho of R and omega, please notice del squared plus k squared makes that operator, it's acting in a world which is C0. And then this is a source. So those 3 point sources are embedded in a whole space which is C0. Yes? Now you have a continuum of embedded sources. It could be continuous, could be discrete. And then this rho, of course, can be written as an integral over Dirac delta, showing that this is what those A's became. The AR prime became this continuous function, and just as rho was this discrete sum, now it's this integral, and then you get this equation. So this equation says something very important, central to everything we do. It says if you have a wave field P, yes, and that you imagine this wave field, the medium is a homogeneous world with sources embedded, yes, sources. Then whatever the right-hand side of that equation was, whatever the right-hand side of the equation, del squared plus k squared, P is rho, whatever, there you go. This whatever this rho is, any function there, you can imagine is a distribution of sources embedded on this homogeneous world, omega over C0, then suddenly the solution P is an integral over rho with G0 plus, whatever the rho is. So it says it's a superposition of waves that leave with speed c0 from every point r prime. In other words, that g0 r prime omega is a wave that's a causal solution from r prime to r. The weight at r prime is rho, but that's just an amplitude, and then it goes with c0. Okay? Understood? In other words, it's a rho at r prime times g0 of r prime, and omega, yes? You just put some number at r prime, rho of r prime, and times g0. Okay. So this is might seem trivial, simple formula. This is a cornerstone of mathematical physics. And it says if you have del squared plus k squared, P is rho. And if you have a causal solution to the problem where instead of rho you had a Dirac delta, then the solution for any source distribution is a linear combination, if you like, of the impulse response from r prime times the weight of the source at r prime. Okay, well that problem is, let's remember what that problem was. A homogeneous world with sources, each exploding with a weight rho of r prime at r prime, yes? Okay, now we have a different equation. Here's an equation where it's not homogeneous. Here the equation is for a velocity c squared of r. It's not c0, yes? We want to exploit that formalism, okay? Exploit that formalism by rewriting that form, recasting that form to make it look like del squared plus omega squared over c0 squared. That's the point. We're going to change. This is propagating with some source rs, with some time function at rs, and this is a wave propagation in a heterogeneous medium. Not c0, c of r, heterogeneous, yes? We're going to reformulate that so it looks like what we had on the slide before. How we do that is write 1 over c squared of r as 1 over c0 squared times 1 minus alpha. And then substitute this in there and put this 1 over c0 squared there and put the alpha over c0 squared on the right hand side. And you get this. Now you're back to del squared plus k squared p, yes? And the right hand side is a rho, yes? And no matter if you give me del squared plus k squared p is any rho, we said we know how to solve it. You just take that rho and multiply by g0 plus and integrate, yes? So this is a different way to imagine a wave field. The normal way to imagine a wave traveling in a heterogeneous medium is finite difference, finite element, lattice-Boltzmann, reflectivity. All of those modeling methods deal directly with the actual velocity, c of r, as it varies from point to point. Boundary conditions are matched and so on. Yes? So this is different. This is an alternate and equivalent way to view the propagation, the wave, in a heterogeneous medium. The way it's viewed is that now you suddenly have a homogeneous world. The real world is heterogeneous. You're going back to del squared plus k squared. You have a homogeneous world, and these are the sources that are embedded in it. So this is where the energy comes from, yes? And this part of rho lives where there's alpha. And alpha relates to when c0 and c of r are not equal. Alpha is not 0 when the actual velocity is not c0. So in the heterogeneous world, if your actual velocity is not c0, then that's not 0 at that r. And then what happens? Then at that point where the actual velocity is different than c0, there's a source. It acts like a source, because that k squared alpha p will multiply g0 plus and generate. What's the amplitude of that wave at that r where the alpha of r is not 0? It depends on alpha of r, yes? In other words, it depends on the difference between actual velocity and reference velocity. And it depends on the total wave field at that point, okay? But it's a different way of visualizing heterogeneity. So when we start to look at deghosting and other methods, this source, that source, yes? Heterogeneous suddenly became a source, yes? Please remember this, yes? This heterogeneous becomes a source, yes? In this picture. So we have this G0 plus with these two terms. Granted, this is a simple acoustic case where the only parameter we're assuming is velocity, and alpha is the a measure of the difference between the actual and the reference. So this part of the P is the field if it was homogeneous, and this is the extra part that's because alpha is there, and alpha is there because it's heterogeneous. Yes, so there's a weighted sum of contributions at r due to r prime with weights here. Now, this is, you'll notice, is not a solution for P anymore, because once you're dealing with heterogeneity, and where the reference and the actual are not the same, yes? Suddenly you have an integral equation. You have P inside the integral and P outside. This is not a solution here. This is a relationship, okay? This generalizes to the elastic case, where the rho here would have parts that involve P to P scattering. S comes in and create a P wave. In other words, this would have, VPP would have changes in lambda mu rho, and VPS would have changes in mu and rho, yes? Causing reflections between an incident shear and P coming out. In other words, P here due to S coming in. In other words, there has to be an S wave there, okay? And a VPS to generate, okay? Okay. So the point is that idea of homogeneous plus sources can be generalized to, here's elastic, it moves to anelastic without a problem. Okay, so here's this equation, a cornerstone equation. There's another equation that comes from a very different origin. The last equation says, this equation says, I'm going to give you the field everywhere. Everywhere, I need you to know the sources everywhere. Source, integrating all the sources, you get the field everywhere. This other relationship comes from Green's theorem, which owes itself to Isaac Newton's thinking. You'll see why in a minute. This does not give you the field everywhere. It says, imagine you're interested in a relationship for the field inside a volume. Okay? If you're interested in a relationship for the field inside the volume, just because your interest is having the field inside the volume doesn't mean the field only cares what's inside the volume. The field cares about everything that affects it, whether it's inside the volume or not. You want to know the field in the volume. The field has its own interest. Everything that affects it has to play a role in its relationship to influences and what it is. So, but you get a formula which is only valid for R in the volume, which integrates over the sources in the volume, whatever those are on the right-hand side, plus a surface integral. This is very different than the previous equation, which had a G0 plus, because it was a linear superposition of elementary causal solutions. This one comes from the fundamental theorem of the integral calculus, and any G0 that satisfies this equation will work here. Any G0, as long as you have a surface integral. So this equation in this form derives several things. One, it derives all our deghosting. It derives separating P0 and PS, the reference wave and the scattered wave. It derives migration where you know the medium and you want to predict the field inside. All of those applications come from this equation. Okay? So let's take that all space solution and then write this equation below it, which is only valid for R in a volume. If you evaluate the right side for R outside the volume, you get 0 for the equation 8. But inside the volume, those two must agree, because the field is a physical quantity. This is only valid inside. This is valid, the first line is valid everywhere, but it's certainly valid in the volume. So in the volume, they must agree. Yes? If in addition, in the second line, you choose G0 to be G0 plus, then you have the same G0 in the two. And then you can take the first equation there and break it up into two parts, integrating over the volume plus integrating over everywhere in the universe outside the volume. And then when you compare this and this for R inside the volume, you have this equals that, and hence that equals this for R in the volume. That's this. This is called the extinction theorem. It's called Green's theorem for determining wave field inside a volume due to sources outside. So this is giving you the contribution. So this is only valid for R inside some volume. What volume? You choose the volume. This is the integral of sources outside that volume, their contribution to the field inside the volume. And this is a surface integral. It says this surface integral gives you the contribution due to sources outside to the field inside. That's very much sounds like Isaac Newton, because Isaac Newton says, I integrate over something and I give you something on the endpoints, the antiderivative. I replace an integral by something else on the endpoints. Instead of integrating on all the sources outside, you give me a surface integral. Okay? That surface integral gives you the equivalent of integrating the sources outside for a point inside. Okay? This is an amazing formula. It gives you, it cares about the field and the derivative on the boundary, on the surface of whatever the volume is. It gives you the effect of sources outside the volume on the field inside the volume without any knowledge of what the sources outside the volume are. That's absolutely amazing. Okay? So this is the basis of our deghosting methods. You'll see why in a minute. Another application is the basis of what we call Stolt-Claerbout 3 imaging, the prediction of a source and receiver at depth as a way to do migration, make them coincident and time zero. You need to be able to predict what a receiver will be in the volume and then the source in the volume from surface measurements. This form that you saw a minute ago, this form here, in fact, this form without G0 plus, just with any G0, you see there's no G0 specified here. Any G0 here will give you the field in the volume. Now, if the source is not in the volume, if RS is outside the volume you're trying to predict, the source is here, your measurements are here, You're trying to predict the field in here, yes? The source is outside. So if RS is outside the volume, this is 0, yes? If, in addition, inside the volume, your reference velocity is your actual velocity. If C0 is C of R, yes, inside the volume, then alpha is 0 in the volume, yes? So you could have a reference velocity which is non-constant, yes, to make that happen. So if the source is outside, and if inside the volume, what you assume for the reference there is the actual, then alpha is 0, yes? This will be 0 if C0 is C of R in the volume. Under those circumstances, the field will just be the surface integral, okay? That's going to be called on. We're going to ask you to please remember that when we get to the new migration methods we're developing here, okay? So we just said this. Okay, so going back to this equation, P is P0 plus G0 K squared alpha P. If we made, instead of A of omega, we made that 1, then P0 would be G0 and P would be G, and you'd get this relationship, okay? Understand, again, this all comes about from that integrating over sources, yes? This is the air gun, and this is the source due to the fact that the actual medium is not C0, okay? So that's a picture of how a wave in a heterogeneous medium can be described, yes? It can be described as a homogeneous world with point sources exploding, yes? The amplitude of the point sources cares about the energy source, okay, for this guy, and for this cares about at any point R prime where there is a non-zero value here, suddenly there's a source at that R prime with an amplitude which is the actual field at R prime due to this source times the difference between actual and reference velocity, then propagated straight from that point with C0. Propagated with C0 with an amplitude, okay? A superposition of those. That's a picture, a very useful picture. It's not the only picture, as I said. The most normal picture for generating waves in heterogeneous media is to predict the field directly in terms of actual properties, not sources. This is saying the world can be looked at as homogeneous plus sources. That's a viewpoint, okay? Okay, so this generalizes. First, we're just rewriting this in some language. You got that G0 and G here. You get this V defined as the difference in these two operators. This is what we call K squared alpha, is the difference between the reference operator and this perturbation on it, okay? So it starts to look like this. So all of a sudden, this became like a motivation. And then we enter the generalization. In other words, that's very tied to C0, C of R, very acoustic sounding, okay? It sounds very specific. K squared alpha is some amplitude of a source due to the difference between C of R. It's going to be generalized now, okay? The generalization comes from what we call scattering theory. Scattering theory is simply the following. It says, let's say you have a medium, and let's say you have a source, and this source creates a wave in this medium, and that wave cares about the properties of that medium, yes? Cares about the properties of the source and the medium it's experiencing. Let's say you change the medium in some way. Any way, move or reflect a change of value of a density at one point, some way change the medium. There will be a change in the wave field. If the medium changes, the wave field inside and outside that medium will change. Scattering theory says, what's the difference between a change in the medium and a change in the wave field. Yes? That's what it is. Perturbation theory. So with that introduction, imagine the original medium had properties that entered a differential operator L0. Okay? Entered this operator L0. L0 has some acoustic, elastic, anelastic properties in whatever you assume the original medium is. And L0 is the differential operator that governs wave propagation in that original medium. That operator cares about the properties, okay, of whatever that original medium is. Then L is, the first line, is a new differential operator that results when some change occurs. Imagine some change in L0, which we're going to call V, some change in properties V, and that change in properties produces a new Green's function or a new wave field G. This equation, which you saw in the last slide, specific for acoustic, yes, with the V being k squared alpha, generalizes using an operator relationship like this. In other words, if you just look at this, if you consider this to be G0, but these being somewhat like inverses of each other, yes? Then G equals G0 plus G0 VG is an operator identity, okay? Where the nature of what L and L0, G and G0 don't matter, okay? They're just two differential operators whose difference is V. So this is a identity as firm as sine squared plus cosine squared is 1 for Pythagorean, for Euclidean geometry, yes? It's, so again, this is, G is on this side and this side. It's not a solution for G. You can turn that equation, this relationship, into a solution for G by a series of iterations. You can say G is G0 plus this. Oh, well, let me put for the first approximation for G, G0. So you get G0 plus G0 V G0. Then you take that and substitute again in for G. Keep doing that, yes? A set of iterations, yes? And you get this forward series with that. This is a very famous, old formula. It's called the Born series by the physicists and the Neumann series by mathematicians. It's a modeling method. This is a way to produce the field G, which is governed by the operator L, in a perturbation form. The normal way to find G is directly in terms of L. That's what finite difference does. It doesn't go to a reference. It solves in terms of actual properties, yes? This is solving for G in terms of L being broken up. L being broken up into V and L0. V enters this description as V, and L0 enters this description as G0. Okay? So this series, which is just an iterative way of seeking to have higher and higher approximations to G, is nonlinear. In other words, it says, if you have a medium described by L0 and you change it in any way by V, any way, doesn't matter how small you make the change. If you have a change V, then the difference in the wave field, G minus G0, is nonlinear to V. V, V squared, and so on, no matter what the change is. That's a very important property. So number one, to generate G, what do you need to know here? First is you need to know model type. In other words, you have to tell me it's acoustic, yes? Then you have to tell me, or or elastic or anelastic. You have to tell me what the reference L0 is so I can get G0. And then you have to tell me what V is. You have to tell me what the difference is between the actual medium and the reference. Yes? So to do the forward series and to use it as a modeling tool, you need to know the model type and you need to know every detail of the subsurface. Okay. Okay, so the first term in that forward series, this term, G minus G0, we call that the scattered wave, the difference wave that's caused by V. And this is then viewed as a series in the scattered wave, where this is the portion of the scattered wave, linear in V, quadratic in V, cubic in V, and so on. Okay, so what we want you to recognize is this modeling form, equation 2, is geometric in nature. That sort of obvious thing is lost on almost everyone who does inversion. Okay, so and the consequences are severe, because this, if we associate G0 with A and VG0 with R, this is AR squared. That's its form. Okay. Now, this geometric series is an algebraic thing of multiplying a number A by a number R squared. And this is more complicated than that. There are integrals and so on. And it will be matrices in general, operators. Okay. You'll see later. But the form here is geometric. And if R in absolute value is less than 1, it has this sum. Yes? And the first term, as we said, this is linear in R. This is the portion of S, linear in R, quadratic in R, linear, quadratic, and so on. Now so we have the forward series is a power series, like a generalized geometric series in V, which we're calling it basically R, yes? And you can take that equation that everyone had in high school and solve it. If I give you the sum and I give you the first term, you can find the rate. Solve that for R. You solve that for R, you get this. You solve that for R, you get this series, assuming S over A absolute value less than 1. Yes? A series. For R, so it says if S is a power series in R, then R is a power series in S. Yes? Where there is a linear, this is the portion of R that's linear in S. The portion of R that's quadratic in S. This is not an approximation to the linear. That is the linear. This is the quadratic. That is the cubic. Okay? Those are direct formulas for every term to whatever order you're interested in finding R, which of course is V. Yes? So one way you could find this, by the way, is you could take this form, R1 plus R2 plus R3, and substitute it. Take that form, R1 plus R2 plus R3, substitute that in here and in here, and then set terms on both sides of the equation that are equal order in S, equal, and you will get R1 is this, R2 is this, and so on. Okay? Okay, so analogous with that, V, so the forward series is predict the field. The forward series, the forward scattering series and the inverse scattering series are perturbation. Okay? They're not giving you anything in one step. They're giving you term by term. So the forward series gives you G, or G minus G0, in powers of V. The inverse gives you V as an order in orders of the measured data. And if you take a form like this and substitute it in the forward, you take V1 plus V2 plus V3, put it in here, put it in here, put it in here, take this G minus G0 and evaluate it both sides on the measurement surface. And where V1, please remember this, V1 is the portion of V that's linear in the data. Linear in the data. Okay? We will, before and in a few minutes, say what data. Yeah? What data, yes? Linear in the data, linear inverse. Because that's a very important issue. Here the data is, we're assuming some kind of simple scalar field. It's the field G minus G0 measured, yes, on the measurement surface for sources and receivers. Okay, so what derives from substituting that form V1 plus V2 into the forward series and making terms on both sides that are equal order in the data equal, you get this set of equations. This set of equations is, look at this, R1 S over A, R2 minus S over A squared, minus S over A squared. You understand? Now, that simplicity doesn't go on because these are integrals, okay? But certainly to the second term, it's just like the algebra equation, okay? Because remember, okay, because this is R1, because R is VG0, yes? So it's like A R1 is the data, A, right? A R1 is the data, you see? Okay, so this set of equations has a profound consequence. It says the following. If you start the problem L0, that's your reference. That's just assume water in the marine case. And G0 is simple propagation in water speed. And what you're looking for is V, the difference between earth and water, V, yes? And it's saying that V is to be expressed as a series, V1 plus V2 plus V3, yes? And after you find each of those V1s, V2, V3, you sum them, you get V, you add that to L0 and you get L. You found the medium, yes? So what the equations of the inverse scattering series say that to find V1, you solve this problem. In other words, if you look at this, every one of these R's is directly in terms of S and A. There's no updating, okay? R2, the quadratic contribution to R cares about the data and G0. A is G0, you understand? So these formulas say that to solve for V1, the first term in the series for V, you need the data and water speed propagation. Once you have V1, you put it in this formula. You have water propagation, something that cares about data and water speed. In fact, you could analytically solve this for V1. Yes, and then all the terms here are water, water data, water, water data, water. So the whole right-hand side here is directly computable in terms of your data and water, water propagation. And then you invert the exact same operator that you did to get V1, you do the exact same thing to get V2. It's not a new matrix to invert, okay? The inverse step is trivial. In fact, it's analytic, yes? The complexity is in multiplies. Multiplies with band-limited noisy data any day prefer over making a matrix and inverting with band-limited noisy data, you know. So this is fundamentally different than iterative linear. Iterative linear, why does people so taken with iterative linear? Because they don't look at that forward series as geometric. They look at it as a Taylor series. Data at m is data at m0 plus data prime of m0 delta m. If they look at data double prime m0 delta m over 2 and so on, delta m squared over 2, as a Taylor series, which is what they're thinking, Taylor series do not have an inverse. Geometric series have an inverse. R gives you S gives you R, because it's geometric. Okay? So geometric is a very special Taylor series. Okay? Very much simplified and allows a direct inverse. So since when they deal with Taylor, they don't know how to invert after the linear, because there's no, it's a Taylor. So they just keep iterating, they keep updating the linear. So the missed opportunity from our point of view is that they're sort of stuck with this Taylor series sort. Okay, we've said this already. Okay, there's a view that solving a forward problem in an inverse sense is the same as solving an inverse problem directly. That I'll take some forward problem and I'll just solve. Here I got the data, PP data in terms of changes in lambda mu rho. That's a modeling method, and I will just take that modeling method and solve it. Use it to solve that forward problem for in an inverse sense. I would like to show you now why that is not valid. That's not equivalent to a direct inverse. There's one situation where solving a forward problem in an inverse sense is the same as solving an inverse problem directly. There's one circumstance where that is the case. That circumstance is very common. We use that very often. It's when the direct inverse is linear. When the direct inverse is linear, then a direct inverse and solving the forward problem in an inverse sense are equivalent. What's an example, a very famous example of a direct problem which is linear? Migration. Migration takes data and you sum it and you produce the receiver at depth. You sum it and you get the source at depth. That's a linear process, and then you get the structure. Yes? There's no data times data. Yes? It's linear. That's why migration and modeling are so close. Yes? So here you have S equals AR, some linear. Assume S equals AR is exact. Yes? If S equals AR is exact, then solving for R in terms of S and A is the same as solving S equals AR in terms of R. Yes? The direct inverse and solving the forward problem in inverse sense are equivalent because it's linear. Let me show you why, if it's nonlinear, that makes absolutely no sense. Okay? You understand what I'm saying? Let's take the simplest nonlinear. The first, assume that the actual problem is S equals AR plus AR squared. Yes? And I say, that's the forward problem. You give me R, I find S. How do I find S? How do I find R? I solve a quadratic equation. I get two roots. Okay? What I just said is you're solving a forward problem in an inverse sense. A forward S in terms of R, I'm using it to solve for R. Yes? I got two roots. Make it AR plus AR squared plus AR cubed. It's a cubic equation. Solve for R. You get three roots. Yes? Keep going. R to the end. You get n roots. Yes? Go on forever. Yes? What's the inverse of S equals AR plus AR squared plus AR cubed? This is the number. You had it two screens back. The inverse of this is, because this is AR over 1 minus R. I solve directly for r. There's one number. This, as you get more and bigger n, you get more and more roots if you solve the forward problem in an inverse sense. The forward problem in an inverse sense is not the same. It couldn't be more different. There's one inverse, yes? This number. The closer you get to infinity here, the more that's the answer. One number. This says the higher you go here, the more roots you get. If I solve that problem, that forward problem in inverse sense. Okay? Okay, so that's a caveat for people who see a forward problem. I'm going to solve that in an inverse sense and think that that's equivalent to solving an inverse problem directly. This is the inverse problem directly. Solving for the roots here will give you n roots. Go to infinity, get infinite roots. Not one. Yes? Okay. So direct and indirect, we've talked about this. And so I think every bullet on here has been covered. We say some words about model matching. You can match anything. And the more you match, things might improve. But how do you know what you're supposed to be matching? Okay. So it's FWI now is doing matching with primaries and multiples. The direct inverse coming from that V1, V2 says the following, and you'll see the exact formulas. It says if you want the changes in lambda, mu, and rho, first, you need multi-component data. Second, only primaries. Okay? Only primaries, and there are explicit formulas for the linear estimates of lambda, mu, rho. The quadratic. There's no finding estimates better linear. There is a linear. It's analytically determined. There is a quadratic estimate of lambda, mu, rho. Okay? Just like that R1, R2 formulas, yes? But it needs primaries. How do I know it needs primaries? Before you get to that, in the inverse series, it let the multiples be removed. If it needed them for inversion, it wouldn't let you take them out. You don't decide from the inverse scattering series what it needs. It tells you what it needs. Okay? It wouldn't let multiples be removed if it needed it for further tasks. Multiples from the point of view of the inverse scattering series, which is the only direct multidimensional inverse method, multiples are a form of coherent noise. Okay, so these are different tasks. And this is saying what happens in the elastic case. In the elastic case, it's the same old business. L, L0, G, G, you know? Except the differential equation begins as a matrix. P and S are coupled. Yes? There are for any heterogeneity, P and S care about each other. Yes? So the operator and the data and the V are all matrices. This is some detail. So the data, instead of G minus G0 measured, is G0, V, G0, G0, V, G0, V, G0. You have matrices here. Okay? That's just the nature of that differential equation. Gives you this. Then the VPPs, which contain all the changes in lambda, mu, rho, yes, are again matrix plus first order in the data. What data? That's what it says. You know what data? That data. Okay. Now, let's say you go to the inverse, and you go to the first term. Here's the first term. Here's how you could get fooled. Stolt and I were fooled. We publish things. Okay. We have a difference of view about what I'm about to say. Yes. This is data is G0, V1, G0, yes? But matrix, yes? So what in the world could be wrong with saying DPP is G0P, V1PP, G0P, yes? That's absolutely true. yes? So you would think, if I want to get VPP from V1 PP, yes? V, not linear estimates of things that are in PP, yes? V1 is the linear, yes? Linear estimate of VPP, yes? That's what the subscript 1 is there for, yes? Linear. Linear in something. We're about to say what's something, yes? So this has changes in lambda mu rho, all linear. The linear estimate of delta mu over mu, sub 1. Delta rho over rho, sub 1. Everything's linear in there. So you might think, well, that equation sits by itself. Here's where you get into an issue that you're not aware of until you look at the full series. How are you going to get V2 PP? Okay? In other words, to get VPP, you need V1 PP plus V2 PP, right? You might think for V1 PP, all I need is data PP. Yes? Reasonably enough from what I just said. But watch what happens when you look at V2 PP. Yes? G0, V2, G0 is minus G0, V1, G0, V1, G0. Same old story. As soon as you look for this, it wants PP, SP, it wants all those other data components. Do you understand? It's the nonlinear that tells you that you can't just take DPP and solve for V1 PP. You must take the matrix, the data, PP, PSSS, and invert that at once. In other words, when we say something is a linear estimate of data, please listen to this. When we say some quantity is a linear approximation to that quantity in the data, the question is, what is the data? The answer is, it must be a data that in principle can directly solve for that quantity without linear approximation. There's a data that can solve for that quantity. And then a linear estimate is something linear in that data. Not some piece of that data. Okay, so that message is that this quantity is the data, okay? Even for, if you want to get changes in lambda mu rho, you must have all the components, okay? Now, someone will say, well, what if I didn't measure PS and SS? Well, the benefit of this is, when it doesn't work, you'll know why, okay? As Stolt would say, okay? You'll know why. And what Haiyan Zhang did when she was doing this with Doug Foster and Bob Keyes, and they only had PP data, she synthesized. She took the PP data, and don't listen to what I'm about to say, she solved for changes in lambda mu rho over PP, and used those changes to make PS data and SS, which cared about changes in mu and rho. Okay? And that was better than putting zeros in. Okay, you understand? Make some data. The point was, there were synthetic tests, and you could see the difference between actual PS data and what was being approximated by that procedure. And that has a cost. Okay? So what's the point here? You have a framework for how to do parameter estimation in the elastic world, where there's a linear, a quadratic, a cubic estimate of changes in lambda mu rho. Okay? What you do about that, what you can't do, at least you know what you should do, what a direct inverse requires of that amplitude analysis. And it's only primaries. Okay, so let's move ahead. We're going to move fast. Where are we now? Okay, we're about an hour in, yes? An hour, more than an hour. Okay. So, pre-processing, deghosting, that's up shallow there. And there's work, Zhen Zhang was showing some of his work. There are other people who were involved in this, Yuchang Shen and Jing Wu involved in this work, based on pioneering work of Jingfang Zhang and Jim Mayen. So what's the contribution here? The contribution, to get to the point, the contribution of the people I just said is, how do you do deghosting when your cable is not horizontal? When the cable is horizontal, the method of Lassa-Amundsen PVZ works. Yes? When it's not horizontal and you assume it is, there are consequences. Let me just show you that. The Green's-Theorem methods do not assume that this method for deghosting is an integral over the measurement surface. Whatever the measurement surface is, this formula for deghosting reduces the PVZ when it's horizontal. Okay? In other words, if you Fourier transform over x and y, you get the Lassa-Amundsen formula. When it's not horizontal, you use this formula on the measurement surface. Yes? And you'll see the consequences. I'm just going to erase due to shortness of time. So this is Zhenzong's formula for that, where he assumes that he has the measurement surface z as a function in x and y. Yes? It's not constant z anymore. It's going to vary. So let's just get to... So this is a data, a free surface, and a single reflector. And this is a horizontal acquisition and essentially using PVZ. So you receiver deghosting. So there's a ghost on the source side and the receiver side. The primary has ghosts and the free surface multiple has ghosts. Okay? So you're going to see ghost removal. Source and receiver deghosting. And this is confirmed by a modeling which didn't have ghosts. Okay? In other words, it's synthetic data. Yes? Then this is an undulating acquisition surface. This is what the data looks like on what the receiver, the traces look like, yes, on that undulating acquisition. This is at a shallower depth what the wave field would be, because when you're deghosting here, you're deghosting shallower than the cable. See, this is receiver deghosting above, yes, where you assume that the data that it came from was horizontal when it wasn't, so you get this degradation. And then the source and receiver, it doesn't get better, so it's a serious degradation. Now, again, this is the data that's from that undulating on that undulating cable. Receiver deghosted, shallower, where you've accommodated that surface in the deghosting. Okay? And this is source and receiver deghosting, where you have accommodated the corrugated acquisition in predicting a deghosted data shallower. Okay? And then there's a recent work that had tremendous help from Dr. Chung Fu on this. What's the impact on imaging? Let's assume you have a horizontal water bottom, you have a horizontal acquisition, and you image it. Yes? And then let's assume that the acquisition as it is on the right, where it's undulating, and you assume it's horizontal. Okay? So the data on the left is horizontal acquisition, yes? The data on the right is non-horizontal acquisition. This is the image when the acquisition is horizontal, and it images the water bottom, yes? This is what the water bottom looks like when the acquisition is this, and you assume there was this. The horizontal water bottom looks undulating. You drill on a structural high here at the water, okay? So this, the third panel, yes, is imaging, imaging, assuming that the acquisition is known. Okay, if you accommodate it, you get the water bottom as horizontal, as if the acquisition was horizontal. Okay, this was led by Dr. Chung Fu, working with Zhenzong. Okay, these images. Okay. The next, Jingwu. Jingwu, again, a form of pre-processing essential for onshore in current application, including very current new methods for removing ground roll. It's without exception they use filtering. And filtering will remove the ground roll, but it removes part of the reflection data. So this contribution of Jingwu is being able to predict separately the ground roll, yes, from reflection data without injuring either. Okay, it's the same kind of formula: P grad G0 minus G0 grad P, separating. Okay, so this is an example of field data with a shot record with the ground roll. It's reflection data. You cut this, you're going to be taking some reflection data with you. So let's just, this is the acoustic case. This is the elastic case. In other words, this is if you're in an elastic medium. So how is this working, very briefly? The world here starts off with a homogeneous world, which is water. Okay? And starting with the marine case, let's say, yes? And in this world, which is homogeneous everywhere, we have things that are not water. Air is not water, air guns is not water, earth is not water. So those are heterogeneities. Okay? Those are places where the actual velocity is not C0. So they are sources. Remember that early slides. Heterogeneities become sources, yes? So there are three sources. There's a source due to air, there's a source due to earth, and there's a source due to air guns. Each leaving, in other words, remember those sources, their amplitude cares about k squared alpha p, but they leave, just leaving with G0 plus always, yes? So the earth, what the earth does is away. What the air guns does is away. What the air does is away. Well, now when you do this kind of Green's theorem and you get the contribution inside the volume due to source outside, the only source that you put outside is the earth. And it's going up. And if you take the output point in the volume below the source, that's the only up. Because the air guns is down, the air is down. So the contribution due to the earth is just Green's theorem. Okay? And that's how you get the up wave. And the up wave on the receiver side is the deghosted. That's simple. So that's what's going on here basically. For when you're in an elastic medium, it gets more complicated. It's not the pressure in the normal derivative, you need displacement and traction. Okay? That if the reference is elastic, yes? On Earth, ocean bottom, we're talking about now. That P grad, that's for water. Remember, water, three sources. Now you're on ocean bottom, that's became the reference. Okay? So Jingwu's great contribution is she tests it given traction and U, and she gets the upfield. In other words, the direct wave, the Rayleigh wave, the ghosts are gone. Yes? And she's getting the reflection part of the displacement up. Yes? Her huge contribution, so she showed this earlier, that this works. What she did this past year was, in the traction is in general, that's what the traction is. It needs all kinds of partial derivatives of displacement. Every component of displacement and its lateral and vertical variation. That's in general not That's not, even if you have multi-component data, you don't have that. It wants rate of change, yes? Okay, especially the vertical one will be an issue. So she said the following: I'm going to synthesize my data. I'm going to take data that comes from air and earth, and I'm going to deghost it, get the ground removal and so on, yes? But I'm going to assume in my theory, the processing is that it's vacuum over earth. The actual data she processes comes from air over earth, yes? Like real, you understand? If you assume in your theory, in your processing, that it's air over earth, you need traction. You need that, okay? She's saying, what would happen if I assume it's vacuum over earth, yes? If you assume that in your processing, then it turns out instead of needing all of those partial derivatives of displacement, of every component of displacement, well, this is showing having, that was when she measured the displacement and traction. This is, I'm racing ahead. Here you have the direct wave, the Rayleigh wave, the ghosts of all the primaries. There are PP primaries, PS, SS, 3 primaries each with ghosts, yes? All of those ghosts have to go, the Rayleigh has to go, it's down, the direct wave is down, the ghosts are down. This is receiver deghosting, yes? The only thing that should stay, if you're looking at the upfield, is primaries without ghosts. And that's what she has, okay? That's when she gave it traction. The big next contribution, she's assuming measured U and T, is she said, let me approximate in the processing, let's assume it's vacuum over earth. If you do, instead of having the need for traction, you only need the wavelet, the source signature, okay? An estimate of the source signature near the source, like a base plate. Okay, that's a much reduced requirement. Okay? So with that, there you go. The traction reduces as long as you say it's vacuum to just F of omega is a signature, a source signature at the source or near the source. Yes? And that becomes, instead of this guy, becomes basically a wavelet. And then the question is, how good is it for deghosting? And she shows very encouraging results. I'll just race to them. Simplified formula means vacuum over earth. Here's the data, Rayleigh wave, all the primaries with their ghosts. And then she gets a very good set of primaries, 3 primaries, yes, PP and so on. And there's a bit of Rayleigh left, yes, but avoiding the need for traction is a big step up, okay, in terms of being able to apply these deghostings to onshore without filtering. This is a prediction. This is not cutting, okay. Okay, so that's her. Okay. Now we're moving to multiple removal, okay. To start the discussion of multiple removal, let's say a few words about primaries and multiples. The methods that are used to determine structure and perform amplitude analysis are called migration and migration inversion. Yes? Migration only has meaning for primaries. I'll repeat that. Migration only has meaning from the very first concept to the most sophisticated methods today for migration only has meaning for primaries. Why? The simple idea was you had a trace, an event on a trace, and that was in time. People realized that was not a XYZ location of that, what generated that event. They wanted to move from that event in time to some place on a reflector that they believed was a reflection that caused that event. A reflection that caused that event. One reflection. That thought is only for primaries. If I say I want to map that event, and that event is a multiple, what are you talking about? all the reflections you're mapping to. Migration is a map. That event goes to a place, yes, it doesn't go to many places. It's seeking a point in its earliest conception. Find a structure map. Find a place on a reflector where that event reflected, and put that event there. Migrate from that place in time to that place in space. That's the idea. Okay, so the primaries come in two varieties: those that you record and those you haven't recorded. For those that you've recorded, there are two methods for migrating. One requires the velocity. We'll talk about an advance in that, and another doesn't require the velocity. The work of Professor Feng Lu, and the advance in the work of using primaries for methods that require velocity. That's the work of Dr. Chung Fu, Dr. Yang Li Zhao, and Professor Feng Lu. Yes. So these are both will be. You'll see the progress in projects on those. Need the velocity, don't need the velocity, okay? So this is some formula. This is that migration method that we'll say some words about later on. That is the method you need to use if you're dealing with discontinuities, two-way waves. It's the first migration method that is equally effective at all frequencies. We'll say something more about it. Just remember that formula. Okay, with that formula, you can show that if you have an accurate discontinuous velocity, and you predict the source and receiver above a reflector, then multiples play no role. They will never contribute to the image. So if you were able to find an accurate discontinuous velocity, you would need to remove multiples. The reason multiples have to be removed is because of the second bullet. In the real world, we don't have, we're lucky if we have a smooth accurate velocity, a macro velocity, call it. And once you have smooth, then every multiple causes a false image and must be removed. So the requirement for removing multiples, if you have recorded data will be recorded primaries and recorded multiples. If you have a smooth velocity, you must remove the recorded multiples. Otherwise, every one of those recorded multiples will give you an artifact with a smooth velocity. That's the state of things, and that's what drives all this multiple removal activity. What about unrecorded primaries? There's a lot of activity and a lot of communication on using multiples. They've been rehabilitated, you know. They're now signal. So these are some of the people who've worked in this. Burkout, Verschoor, Shan, Whitmore, Valenciano, Nizar Chimengwe. So what goes on there is the following. If you have a recorded multiple, and if you are able to have this sub-event, this part, this solid line sub-event also of that multiple, you have the multiple, and you have this sub-event, then you can get an estimate of this primary's image by taking this event and make it go forward and take the multiple and make it go back to get some approximate image of this assumed, the dashed line there is assumed to be unrecorded, okay? So there are, first of all, that has use. We've seen examples where it has use. As with everything, it has issues. The first is, how are you going to get a recorded multiple? To have a multiple predicted, I need the sub-events. I got to have the sub-events. Otherwise, I don't know that it's a multiple. So how is, yes? To be able to predict that multiple, I need this and that recorded. Yes, otherwise I don't know it's a multiple. So how people deal with it is they recognize that, so they put all the data in. They said, we put all the data in, then you have multiples and other things. Yes? And those other things cause issues. Okay? They call it crosstalk. Yes? So that's one issue. But here's another issue. Let's say this was the recorded multiple. Yes? And let's say, again, that you measured this. You measured this, and somehow you had this. Yes? That multiple was recorded. You had it. And you had this event here, which has a ghost on it. Yes? You remove the ghost here and keep the ghost on that side. And then, but the unrecorded here, the assumed unrecorded here, is a multiple. So if I do this kind of take this forward and take this back, take this forward and take this back, you're going to get an artifact. You're going to be RTMing a multiple. You understand? You're migrating this. Yes? That will give you an artifact. So that's an unrecorded multiple causing a problem. Yes? An unrecorded multiple. So before migrating recorded primaries, recorded multiples must be removed. Why? We said why. Because it's smooth velocity. Use a smooth velocity. You just take your data. Every multiple that's in that data, if you migrate it with a smooth velocity, is going to give you an image. And there's no structure there. So before migrating recorded primaries, recorded multiples must be removed. Before finding an approximate image of an unrecorded primary subevent of recorded multiple, the unrecorded multiple subevents of the recorded multiple must be removed. In other words, this has got to be removed in order to be able to do this kind of thing. To take this forward and that back, this must be a primary. If this thing and this together give you this as unrecorded, and you take this forward and this back, you're going to get an artifact. You're migrating a multiple. Yes? So if you want to do imaging of recorded primaries, you got to get recorded multiples out. If you're doing imaging, approximate imaging of unrecorded primaries, yes, you must remove unrecorded multiples. Okay? Multiples are never migrated. Okay? So there's a nice symmetry to it. So even when you use, let's say in this case, let's say here I got this multiple and I used it to get an approximate image of that unrecorded primary. That multiple itself is recorded, must be removed. In other words, I have to remove it to deal with recorded primaries. Yes? So at the end, every multiple, recorded or unrecorded, must be removed. But they could have sub-events which you can get an approximate image of. Yes? But at the end of the day, the multiple itself must be removed. So to give some distance to this issue, the idea of getting an approximate image of an unrecorded primary is because you haven't recorded adequate primaries, right? So in the history that many of us have been involved in dealing with inadequate data, trying to twist and turn theory to accommodate a 2D world where it really was 3, with asymptotics and other approximations, eventually, those things were useful at the time, but eventually we understood you had to acquire the data. Yes, you just had to acquire the data. Yes, and that trend, you know, we had 2D collection plus asymptotics, single component onshore, yes? Single cable methods to do wave separation. We were all involved in these kinds of things, but eventually acquisition came to replace those. We just get the data. So we can anticipate if the need for the value in unrecorded primaries gets to be recognized as serious enough, or the broad enough circumstances, we're going to have to do more acquisition, record more primaries. That's the best way to get an approximate. There's no substitute for a recorded primary. Okay. Okay. So multiple attenuation elimination. The two types of multiples we maybe could we take a break? Now that we've established that multiples, both recorded and unrecorded, need to be removed for seismic processing, whether or not you use a multiple to get an approximate image of an unrecorded primary or not, the multiple itself always must be removed. Then the question is, what is the state of multiple removal, and what is this industry status of that, and what is MOSRP doing about open issues? So this, we catalog multiples as free surface multiples or internal multiples. A free surface multiple is a multiple that's had at least one downward reflection at the air-water boundary. An internal multiple has had all of its downward reflections below the air-water boundary. Okay? So for free surface multiple removal, the method from Delft, SRME, is the industry standard. And that is an effective method, in particular when you have an isolated free surface multiple. The SRME does not require subsurface information, does not. It shares that with the ISS free surface algorithm. SRME does not require subsurface information. However, it predicts an approximate amplitude and approximate phase of the first order free surface multiple, and the error increases with offset. Okay. So the way that's addressed in practice is by using that in conjunction with energy minimization adaptive subtraction. So if you have a free surface multiple and you have an SRME estimate and you're interested in removing it, the idea is that if that multiple would be removed in some region of space and time, you'd have less energy, however you're going to define that, in that region with the multiple gone than with the multiple present. So you seek to adjust the prediction using that criteria to remove the multiple. And that is very often successful. Okay, in many cases that's successful. When it won't be successful is when you have interfering or proximal events to the free surface multiple. If you have, for example, a destructively interfering primary with a free surface multiple, the energy when that multiple comes out could be bigger than when the multiple is there, because it had destructive interference. So the criteria itself behind energy minimization, adaptive subtraction, fails under many circumstances where you have proximal or interfering events. I'll repeat that. The criteria behind energy minimization, adaptive subtraction, will fail, independent of the implementation. Doesn't matter what LP norm, the criteria that you're aiming for is not valid. Okay. So given that, what's the MOSRP response? The inverse scattering series free surface algorithm developed by Paulo Carvalho et al. Predicts the first and higher order free surface multiples with the exact amplitude and exact time at every offset. It requires source and receiver deghosted data. Yes, requires that. However, if you satisfy those criteria, then it will surgically remove a multiple that's interfering with another event. It's more expensive than SRME, but it's a toolbox option that we advocate people to look at. In addition, we're looking at a new criteria, a new adaptive criteria, not energy minimization, that derives from the free surface algorithm itself. Something to accommodate the fact that the physics isn't what we assume, yes? But that criteria aligns with the free surface, it derives as a property of. So you're driving a parameter to make the data adjust to make that algorithm work, yes? But you're giving a channel for noise, if you like. Okay. So, we're looking at circumstances where the free surface multiple, and we're told that there are more than a few cases where free surface multiples interfere with other events. So this is not an anomaly. This can be frequently occur. And so again, if you have a situation like this, SRME should be your, or could be your toolbox choice plus adaptive, yes? The free surface multiple by itself. If you like this, beware, okay? Then you want to pay more to have an algorithm which can predict and surgically remove without the need for an adaptive criteria, which could be invalid and damage that primary. So this is the Carvalho et al. Algorithm. D goes to data here and here. This factor here is what's missing. Q, the obliquity factor, times e to the iq, epsilon g plus epsilon s. That's the factor that's missing from SRME. If that factor is missing, it's faster. It moves right to x omega. When that factor is there, going to x omega is more difficult, more costly, yes? So what we're suggesting is for times when you have interference, take a look at Carvalho et al. As another toolbox option. Don't, in some knee-jerk way, say it's SRME plus adaptive. Like everything, including all ISS methods, they have a region of usefulness and where you wouldn't go, yes? Okay, so this is a work, well, this is for history, seeing Carvalho's first, this is for a shot record, seeing the original data and then free surface multiples removed. When I was in Brazil with Carvalho, he was a student of mine, and then I went back periodically to ARCO, and they saw these results, in particular this result. The left panel is the data, the middle panel is Carvalho's free surface multiple removal, the right panel is FK filter, which cut everything in a certain direction. Al Hakim, who's the manager at ARCO, said, I don't know what you're doing down in Brazil, but we want this method. In other words, they looked at the data and they saw what this was, yes? This was a very impressive result. You know, cleanly cuts, yes? And keeps the primaries there. Okay, so this is the work of Chow Ma, looking in detail at what a comparison of what the Carvalho ISS free surface algorithm and SRME will do under very controlled data circumstances. So this is the input data. There's so the first order algorithm does two things. It eliminates every free surface, that data does two things. It eliminates every multiple that's hit the free surface once, and it alters all higher order multiples to get them ready for next terms. So when you see this second order, even though we're applying a first order algorithm, there'll be an alteration, but not a removal of the second order. Okay. So this is from Carvalho on the right, a prediction. This is the removal. So you see that it's gone. the free surface multiple is gone. That's the free surface multiple. This is going to be removed by Carvalho. Okay? There's Carvalho. Now SRME. Prediction from SRME. Result after SRME without adaptive. The free surface multiple is still there. It needs adaptive to kill that. Yes? And in this case, it would probably work. It's isolated. Yes? But it gives you an example of one needs and one doesn't need the adaptive. So if the adaptive criteria is the issue, one of them allows you to avoid it. Okay? Okay, so this is showing the difference. Again, this is Chalmers' work. This is ISS, Carvalho. This is SRME. This is Verschuur, Burkout. This is showing the perfect match to the first. This is the primary. The prediction doesn't affect the primary. Just predicts this first order multiple perfectly. And here it's approximately, the SRME is approximately getting that first order at 500 meters. And as you go out and offset, the SRME gets worse, whereas the ISS retains equal effective at every offset. And yet, the biggest difference in here, perfect match. Okay? So, where there are, in this consortium, there are codes, 2D and 3D, with free surface ISS. Okay? Well, what we're proposing is that for companies that have interfering free surface multiples with other events that they rather not injure, that we talk to each other about how to develop a plan to work with companies on plays where this kind of thing matters. Okay? Okay, this is internal multiple attenuation. So let's go back to free surface. Free surface, SRME from Delft does not require subsurface information. ISS free surface from Carvalho does not need free subsurface information. One gives approximate amplitude and phase. One gives the exact, in principle. Okay, in the real world, you need adjustments. When you get to internal multiple, everything changed. That's when ISS got its place, because inverse scattering series internal multiple attenuation was and remains the only algorithm that is able to predict the exact time and approximate amplitude of every order of internal multiple without subsurface information. Delft's methods require subsurface information, some knowledge of generators, yes? And that's where things separated. And so this is the internal or multiple attenuation algorithm pioneered by Araujo and Carvalho, Stolt, and others. These are the companies, among the companies, and we know now that TGS is also coding this up, the ISS attenuator. These are companies that sell that ISS, internal multiple attenuation, as a service. Schlumberger, CGG, PGS, and now we know TGS. Okay? So it's mainstream. If every service company we know, sponsor or not, is providing that service, and these are references to it. This is for Matson, did the first internal multiple marine, and Yilo, Chongfu, Eyal, the first onshore internal multiple, onshore internal multiple attenuation. Okay, so this is the famous challenge data set that Bill Dragoset organized a workshop. Mississippi Canyon data. The problem here was an internal multiple was interfering. An internal multiple was interfering with a base salt primary. Complicated. In other words, you wouldn't want to have to pick which is the internal multiple. The algorithm does that for you automatically. Okay? That's extremely complicated to interpret. Yes? What's going on there? Okay, so what you're seeing here in this cartoon is this top salt, water bottom internal interfere with this, the base salt primary. Yes? And this is a Matson result. This is the first marine internal multiple attenuation. This is Chung Fu Yi Lo work onshore, Saudi Arabia. Okay. Estimate internal multiples. And their conclusion was that other methods couldn't match the ISS attenuator in effectiveness. And that was the conclusion of Saudi interpreters. So the internal multiple attenuator is being used, but it's an approximate amplitude. And what people do to deal with the actual internal multiple, again, they come in with energy minimization adaptive subtraction for the ISS attenuator, because it doesn't have the right amplitude. So again, that is the state of the art today. And it's effective when you have an isolated internal multiple. If you have an internal multiple which is interfering with another event, which can frequently happen onshore Middle East. There are people who think every primary in the Middle East has an internal multiple sitting on it. Then that's not Yi Lo, to quote Yi Lo. He said the biggest impediment to dealing with internal multiples right now is the energy minimization adaptive criteria. That's the problem. He said that a long time ago. So in response to that challenge, there's a strategy for onshore, in particular, the prerequisites that you saw. Deghosting, the Jingwu ground load removal, yes? You have to do those things well. If you start messing up your data by doing some filter, yes? And you have all this nonlinear data talking to data, and you've cut through it, yes? That's not recommended, yes? So, so there are three parts to this strategy. Do the pre-processing that the internal multiple methods, that the ISS methods need, deghosting, direct wave removal, Rayleigh wave removal, yes, and so on. Get that first done and do it effectively. Then make the predictor stronger. And then the work of Yang Li Zhou, Chow Ma pioneered making a more effective predictor, yes? And then we need, as always, a new adaptive subtractive criteria, yes, to fix things. So, let me just show you the results. This is the first formula is for 1D for the attenuator, and there's an adjustment on the middle integral to make it an eliminator. And there are people in the history of this that are listed in one of the slides, okay? There's a history of people. Okay? Ramirez, Wilbur Herrera made a very important contribution. So this is for eliminating all first order internal multiples, okay? Not just at the shallowest reflector. So this F depends on this, and this depends on G, and G is down here. Okay, so it's complicated. This is the multi-dimensional version of it, and let me just show you results and move on. This is a multi-dimensional example. That's a base salt primary. That's an internal multiple, very similar to the one in Mississippi Canyon. Downward reflection at the water bottom, upper reflection at top salt, yes? And they interfere. They're made to interfere in this model, yes? So when you look at the data, you can hardly see the base salt because of the interference. See this? Yes? When you do internal multiple attenuation plus energy minimization is you're not recovering that base salt. And then when Yang Li and Chow Ma do the elimination, they recover. So that's the point. It's there when you have the interference, and where the ISS internal multiple attenuator plus adaptive is not appropriate. Yes? Not the tool. Okay, there's other issues that Dr. Chow Ma and Hong Liang contributed to, with how to deal with the input being primaries and internal multiples, and their comprehensive theory, together with Yang Li Zhou, accommodates issues that can arise, false predictions from the ISS attenuator when you're in when the input is an internal multiple itself. Yes, that issue will arise, can have a high likelihood of arising if you have many generators. If you have 2, 3 generators, if you have 2, it won't occur. If you have 3, the more generators, the more likely that issue. So if you have 1,000 generators, do what Dr. Chow Ma tells you to do, and that will remove that issue. The spurious events that come from internal multiples being treated as sub-events in the B1, B1, B1. Yes? So I encourage you to see their talks at the annual meeting that there's a link to. Okay, migration. Migration, we're interested in, so we're moving from multiple removal to migration, down here. Stolt migration and then ISS migration with a velocity, without a velocity, okay? So this is going on longer than I expected. Let me, let's talk about this. If you're talking about wave methods for migration, this is a very serious statement. If you're serious about migration, I suggest you start by going back to 1971 and reading John Klebau's paper about the imaging conditions. The history of migration did not start with RTM. People act like Kleenex and tissues. RTM is a method, okay, that had a certain benefit, but it has issues, very serious issues in terms of resolution. So I think sometimes we make a mistake that we don't go upstream enough in terms of looking at our migration methods and multiple removal methods. We take some latest, greatest version of things and treat that as that's the starting point. Let's see what we do about it. So the point is there are 2 pieces to wave equation methods for migration. One is what's called an imaging principle. The other is a wave propagation model. Imaging principles allow you to locate. There are 3 imaging principles listed in John Klebau's 1971 paper. He doesn't claim that he invented them, but they're in the paper. We refer to them as Klebau 1, 2, 3. Exploding reflector model is for zero offset data. It's Dan Lowenthal invented it. Yes. So we're yes, but that's only for stacked data. Only okay. The imaging condition 2 and 3. Imaging condition 2 says take all of these conditions were for one-way propagating waves, meaning a wave moved down and a wave moved up. Okay, no diving waves or anything like that in the original thinking here. So the idea was the original idea in the second imaging principle is you took your data and you moved it back in depth. Move it back in depth, your data back, and you take the source field and move it forward in depth until they're at the same place, the same time. Okay, back and forward till they coincide, and then you're at a reflector where this it starts to come up and this is going down, that's a reflector, that thought, okay? So that's the time and space coincident of up and down going waves. The third imaging principle is predict the source and receiver at depth. Predict from surface receivers what a receiver would be at depth. And then predict from sources here what a source would be at depth. After you have a source and receiver at depth, make them coincident and small time, time zero. And if when you do that you get a non-zero result at a certain point, you have a reflector. Okay, it might seem to you that 2 and 3 are very similar. Take the data back, take the source field forward. Please understand, the second imaging principle is the source field forward for a given source. The source is not moved in, okay? It's field. It's one source here, and it generates a field. And that's made to be time-space coincident with the data, okay? Claerbout 3 predicts the source here from all the sources using Green's theorem, yes? It's not one source find its field. So they're very different on the source side and in practice on the receiver side as well, yes? So these imaging principles, this is Stoltz's realization of Claerbout 3, predicting the experiment at depth. Stoltz extended that 2 ways. One is he relaxed the zero offset to get amplitude information, and he also put a scattering theory, what we would call V1, there, so that he could image specular or non-specular reflectors and do amplitude enough. He could do an image of pinch out. In other words, if you have a curved reflector, there's no plane wave reflection coefficient. A plane wave does this. Okay, so Stoltz introduced a point reflectivity, we would call it V1, from scattering theory, and also allowed for amplitude analysis immediately from whether it was specular or not. Okay, that is only achievable, those extensions are only achievable from Claerbout 3, the prediction of the experiment, not from 2. 2 can be extended, but not to that. This is Claerbout 2, where R is the data back and the S is the source field forward. And this is the, when you do Claerbout 2, like in RTM, what happened with RTM? The major contribution of Whitmore and others was, instead of going back in depth, they went back in time. See, time, and if you have one-way propagation, back in depth and back in time are more or less the same. But if you have a diving wave, yes, back in depth is not the same as back in time will go like this, yes. But back in depth, it just keeps going deeper. It's not going to go deeper and then shallower, okay? So the big plus that RTM, which came from Claerbout 2, is that it went to go back in time, yes, which allowed two-way. But these two could not be more different. When you, in principle, RTM, you take the data back, you take that single shot forward, just shot, not shot down, shot field. It's supposed to be an image. You bring this down, you bring the source field, you should get an image. You don't get a consistent image, even for a single horizontal reflector. So what they do is they sum over sources, as if it was a noisy algorithm, okay? Okay, they sum over sources. This sum over sources is to make something consistent looking. There's no physics to it. This sum over sources in Claerbout 3 is to bring the source down. There's an integral over sources with Green's theorem, just like you integrate over receivers to predict the receiver in the volume, and so on. So, very different. This is Yang Lizhao, and okay. So how do you know? So there's one of the things we're interested in is resolution. One of the reasons that there's a keen interest in Professor Mark Meyer's work is if you have more low frequency, you can have improved resolution. Yes? The side lobes will be reduced. Yes? So one issue, though, is what happens to different frequencies when you migrate. So it turns out that without exception, every single current migration method makes a high frequency approximation, either in the imaging condition itself or in the wave propagation part. What that does is it discounts the value in terms of resolution in the image. Even though you get broader bandwidth, you're not getting full benefit. So we've developed the first migration method that is equally effective at all frequencies to be able to provide the benefit at the target that new acquisition for low frequency will provide. Yes? Full benefit, okay, not partial benefit. When you have a high frequency approximation, does gathering more low frequency help? Yes. It doesn't help as much as it ought to because of that high frequency prejudice, okay? When you have a migration method, as you'll see, that is equally effective at all frequency, it helps more, is the point. You get full benefit. It's not that you don't get benefit now, you don't get the anticipated benefit, okay? So how do you know a migration method is high frequency? If you have a picture like this in your migration, if you have one trace, and you say, for that one trace, where does that migration method produce an image? You know, a source and receiver, and you have a reflector, and you have one trace. Where does that trace go? If that trace goes on a travel time ellipse, that's a high frequency. Because what that's saying is, this is the locus of candidates of where structure might be. That picture only makes sense if you believe in ray theory. In other words, this plus this, that time is that time of your trace. You understand? That's a ray theory picture. So as soon as you see a picture like that, you know there's a high frequency approximation. So here's the work of Yang Li Zhou comparing Claerbout 3, the predicted experiment, with RTM, with Kirchhoff. Both of these show candidates, both are high frequency approximation. This is well known. Kirchhoff is well known to be a stationary phase approximation of Claerbout 3, yes? Which is a high frequency approximation. It's not well known that RTM is a high frequency approximation. That upsets a lot of people. I'm sorry for that, but that's just the way it is, okay? That picture says RTM is ray theory, has a ray theory ingredient, high frequency approximation. This says Claerbout 3 and Stoltz extensions do not, okay? In other words, when you do the predicted source and receiver at a given point, you don't get candidates. At that point, if zero offset, at time is zero, you get a non-zero value. There's structure there. And if you get zero, there's no structure. Yes or no. No candidates is high frequency. Looking for constructive interference of possibilities is ray theory. People know that Kirchhoff is that. People don't know that RTM is that. That's very disturbing. But that's just the way it is. Okay? You'll see consequences. So here's another. This is recent results. These figures are recent figures from Dr. Chung Fu. In other words, so how do you know a migration's high frequency? If you did stationary phase, that's high frequency. If you see a travel time picture of possibilities, that's high frequency. Another is if in a homogeneous medium, a wave will move from this source to this in one direction, in homogeneous. Yes? If you have a reflector here, discontinuous in other words. This comes down, and at this point you have in other words, not one-way propagation. A piece is going up, a piece is going down. It's discontinuous. It's one way till it gets here to this reflector, and then it's two-way, yes? So people are aware that homogeneous is one and discontinuous is two. What is not as is if you have a smooth velocity, and you assume for this smooth that at every point that it's moving in one direction, then you've made a high frequency approximation. This is what anything that's not a high frequency approximation looks like in terms of propagation at every point. So it's not enough to say, well, it's two-way. Yes, it's down and up. RTM, we go down and up. What do you mean it's one way? It's one way at every point on the way. It's in the micro, it's one way. Macro, yes. It's in the micro, it's made a high frequency approximation. Not only in the imaging condition, but how the wave propagation model is. Okay. So let me just get to, there's a formula that we have. I'm not going to go through all. This formula is a way to do predicting the source and receiver at depth in a heterogeneous medium, yes, without assuming one-way propagation. So I'm not sure. Maybe I'll race through it. The idea is you want to predict. Remember several hours ago we said the wave prediction for the field inside a volume is given by this formula as long as you know the medium, yes? Alpha is 0 and the source is outside, so you just have a surface integral. And you pick any G0. So this is a closed surface. That's a closed surface. George Green didn't say something about this predicting in. A closed surface with information predicts the field in. If in your region that you're trying to predict the field, your wave is moving in one direction at every point that you want to predict it, it's moving one direction, up, then you can show that if you choose an anti-causal Green's function in that integral, in this integral, choose G0 minus, then for a wave that's going up, then only the upper surface will count and the lower surface will give no contribution. So you need the closed, but if it's up and use anti-causal, only this contributes. But what if it's now going up? What if it's two-way, like we're saying? Smooth varying, moving in two directions, yes? Then anti-causal is not going to be just giving you the information from the top, yes? If you have two-way, what you must do is you must arrange the Green's function and its derivative, both, to vanish on the bottom. In other words, you arrange that, yes? Two conditions. And when you do that, then it requires data. In other words, the field times the normal derivative of the Green's function and so on. If I make the Green's function and the normal derivative both vanish on the bottom, I don't need data there because there's no place for data, yes? The only integral is on top. But you must use the Green's function that has those boundary conditions. That's what we call G0dn. That, G0dn. So one of these brings the receiver down and then you bring the source down. Double Green's theorem, yes? With boundary conditions on the bottom that the field, the Green's function and its derivative vanish. And Professor Fang Lu has pioneered numerical methods to arrange that. This is Chung Fu's result of imaging above and below. Once you're below and you put the source and receiver below the reflector, you have a discontinuous medium that you migrated through. Yes, it's two-way waves above. Yes, so Chung arranges the Green's function and the derivative to vanish. Yes, and predicts the light is imaging from the top, and the dark is bringing the source and receiver below. When you try to do that with RTM, you get rabbit ears. You get all kinds of issues that they have artificial ways to try to remove. Yes, Facci Lu, Scott Morton, yes, Jacques Levé published papers on that. There's no rabbit ears here. You just predict and predict. So part of the plan is to apply this new migration to discontinuous velocities rather than work hard for discontinuous and then start to smooth because we're worried about rabbit ears. There's no rabbit ears in STOL 3, C3. Okay? So this is the slides up to this point are meant to convince you that RTM is a high frequency approximation, and the double people call it datuming, redatuming, predicting the source and receiver at depth, that is not. Okay, that is not. So the question is, can you quantify what difference does it make? One's high frequency, one is not. What difference does that mean in terms of resolution? So this is work of parts with Chung and Yang Li, part with Yang Li and Chung, yes, and then part had contribution from Professor Fang Lu as well on some of these results. So here's a broadband and conventional. This is a spectrum, okay? Broadband has more low frequency, yes? This is the wavelet. The conventional, you see, this in the broadband, the side lobes are reduced. No surprise. Whereas the conventional has, the side lobe is some kind of indicator of lack of low frequency, yes? In the data itself, yes? And then in the image itself, it plays the same role, okay? Single reflector, broadband, conventional. So the point here was that for RTM benefited by broadband, okay, as I said, but it benefited by a 50% reduction in the side lobe, whereas the double downward continuation, STOL C3, had an 80% reduction. This is a single reflector, a reduction of the side lobe by a more significant amount. The issue, though, is now what about two reflectors? Those side lobe reductions are going to affect resolution. When you can see 2 versus 1 is all dependent on those side lobe reduction. So let's race to that. Here's the wedge. So this is RTM, broadband, conventional, and then Claerbout 3, broadband, and seeing under what conditions we can detect 2 versus 1, yes? Same velocity, the data is, the imaging here is done analytically. In other words, this is entirely an imaging issue, imaging principle issue, not a propagation issue, which is another issue, okay? In other words, we want to isolate just the, yes? So here you see the RTM for different widths. Yes, here's the single reflector as a benchmark. In other words, can we see 2 of these? Yes? In other words, this is 1, this looks like 1. It's 2. Because it's too close. You understand? This is actually 1 image, yes? This is the image of 2, but they're 12.5 meters. Then when they start to get further apart, suddenly you can see 2 of these. You see? In other words, you need this to know what 1 means. Yes? To know what 2. So the If it was bigger than 50 meters apart, you could tell too. And then for conventional, it had to be bigger than 75. In other words, if you had broadband, you could tell that there was two reflectors that were closer, yes, because the broadband had more low frequency. The side lobes were reduced, not as much as for the C3, but reduced. Okay, broadband versus conventional RTM. Now for this, yes, this method is not high frequency. This is a high frequency approximation. So again, as I said earlier, it doesn't mean RTM doesn't get value from low frequency. It doesn't get as much as it can, as it could. Okay, so this is C3 for broadband. Again, this is what, in order to know what's resolvable, you need to know what one reflector looks like. Yes? Actual one reflector. And then here already, you can see two. Here not. Yes? If it was wider than apart than 25 meters, you can see two. Yes? And for conventional, 50. So in each case, for broadband and conventional, this is able to resolve where this can't. Okay? That's important. And this is for perfect propagation. When they're doing the contribution we're making is to the propagation model, the G0. Okay? So the benefit yet that what this formula is providing is not yet here. These results could have been shown if people realized RTM was high frequency before we came. Those imaging principles were there a long time ago. What we're doing is arranging to not make a high frequency approximation and arranging the experiment. Yes? Whereas RTM makes high frequency approximation. One way, one way, one way. Yes? We're not doing any of that. So the results you see here, as they're being tested now with V of Z, are going to be more pronounced for the value, the resolution improvement. Okay, so one question is, we have, how do you know when you have V of X, Y, Z? And this is all numerical, G0, DN, series and step size. How do you know you've actually arranged this to be equally effective at all frequency? That was like a problem for me thinking about that. Because there's one thing saying, oh, I got G0, DN, you know, it's two-way, but you're doing things numerically. So there's a way that I came up with, which exploits the interpretability of Stoltz C3. Its physical interpretability gives it a huge advantage, which is when you are predicting above this table what a source and receiver would be, and you ask for small positive time, all that image cares about is where it is and what it's reflecting off. It has small time. It can't, that image by Claerbaugh's thought was, I want a local property. Okay, that's why he's asking for small time. So if you have C0 over C1, you know what, in other words, let's say you have this V of X, Y, Z is your velocity. You've worked hard, and that's your velocity model, and you want to make sure that you migrate through it with Stoltz C3 equally effective at all frequency. This is what you do. Okay, what you're really interested in, this is salt. You want to well resolve a target below the salt. That's your objective. That's the real objective. You found this and you don't know this. Yes? But what we're proposing is the following. Take this velocity that you worked hard to find, yes? And imagine it sitting above a C0 over C1. Yes? Just imagine that. And you're going to model that. And then imagine a case where this is C0 over C1. Homogeneous. This image here, with the source and receiver predicted going through this with analytic prediction of the receiver and the source, what that image has to be must be what this is when you go through it. Because this source and receiver here must only care about this. So if you've gone through this with all your numerical scheme of number of terms and step sizes, you adjust the step sizes and number of terms such that the eventual prediction through here agrees with here. And this, you know, is equally effective at all frequency. Okay? Once you have that scheme of the step sizes and number of terms in these expansions for G0dn, you take that G0n and bring it over to the real deep water Gulf of Mexico where you're looking for this. Yes. You use this, yes, to make sure you've predicted through here, right? Because you know this analytically. Okay? You know what the image, that image better agree with that if it's going to be equally effective. So once you have that, you know how to get through here. So that's what Professor Fang Lu has demonstrated. This is his actual medium. This is the C0 over C1. Yes? The actual is this. It's like a salt thing. Yes? And he used this to calibrate. In other words, getting through this numerically is non-trivial. But he knows the answer. He knows if he had a source and receiver down here, it has to be the same as C0 over C1. He adjusts all that G0dn to make that happen. Okay? And that's, okay? So that result is that. In other words, that's a piece of the image, okay? That comes from C0 over C1 and his numerics overlapping. Okay. And since the C0 over C1 you know is equally effective, you know the answer. Make the numerics agree with that, and you've gone through equally. Okay. Because it's not enough to say G0dn, I want it to vanish along with the derivative. How do you numerically assure that equal effectiveness? Yes? There's a numerical issue. It's not a Green's theorem statement. Okay. So let's race through this topic many have seen. This is ISS. What you just saw is advances by people within the group of migration methods which will be more effective at resolution and amplitude analysis with a known velocity. Yes? This work is the work you might have seen before on ISS depth imaging without a velocity. This work, Simon Shaw, Chris Innen, Zicheng Wang, Fang Lu, among those who contributed. Jingfang Zhang. Okay, so this is Simon Shaw's result. This is a 1D model. This is a water speed image, and this is those V1 times V1 multiplying that you saw in those early slides, V1, 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 V1. You're going to see this picture multiply itself and talk in a way to take these mislocated images and make them locate. This is, thank you. So this is the movie, famous movie now, where terms in the inverse scattering series imaging activity act. And they only act when they determine that there is more need for their contribution. So this one is deeper, but it has less of a velocity, less of an imaging error, because this suddenly had a velocity lower than water speed, higher, higher, and then lower. So the overall error that this has is less than this has. So this required more input, more terms. The amazing thing to me is it decides when it has enough and won't take any more in. This got quiet, and this kept on needing conversations. We call that group therapy, you know. So maybe we could repeat that. This is the action of the. So you see, this guy calmed down, where this one kept needing attention until it became the right location. That's absolutely mind-boggling. That it decides when some term in the series is needed. If someone says, how does it do that? How does it do that? How does it determine whether, how does a term determine whether in some image its capability is called for? There's one answer, one word answer to that. The word is direct. The inverse scattering series is direct. Every single term has got an objective, a purpose, and it decides on with your data whether its purpose is called for. For example, if you give me one primary, just one primary, and you say, take out the internal multiples. At the second integral, it'll tell you don't have internal multiples. It's not matching and looking and searching. It decides first, is the issue that it's responsible for called for? And if it does, it acts. And when this thing stops working, it tells all the higher order imaging terms, not stop. And, okay. So this direct, indirect, don't underestimate that word direct. It's purposeful. This is purposeful perturbation. It's not change and change and change. It's every term in the inverse scattering series has a purpose, and it decides in your data and for its task whether its purpose is called for. Okay. This is the same. The pre-stack. Interesting. Okay, that's the pre-stack version. Again, this got flat, common image gather flat, this kept working. When the common image gather is flat with different offset, and you'll see Mammootty examples with this. When the common image gather is flat, it means it has enough terms and it stops. Okay? When it had that move out, when this move out was here, it needed more terms till it got flat. When it got flat, with different angles, this is a 1D example. Okay? This is looking at different angles for that image. Common image gather looks at different subsets of the data, yes? And if you have the right depth. So common image gather, please understand, when you do traditional common image gather, you're using it for migration methods that require a velocity. And you can't find it. If you could find it, the velocity, you wouldn't be using common image gather. Common image gather is a way to try to determine if you have the right velocity, yes? As by a condition that the right velocity would satisfy, yes? And that's true. It's a necessary but not sufficient condition for a method that requires a velocity. These methods do not require a velocity. When the common image gather is flat, it means a direct imaging without the velocity has done its job. Necessary and sufficient. Totally different. Okay? So here's the famous Feng Liu salt. Here's the water speed image. Here's Professor Feng Liu's higher order imaging series. Here's Zicheng Wang's plus laterally exclusive terms. These algorithms are extremely fast. Those multiple elimination, they're going to melt your computer. Okay? This is 30% longer than a single water speed migration. A single water speed migration is rocket fast, lightning. fast. Professor Fang Lu's closed form here, yes, outputs an approximate image in almost no cost. Here's full shadow, water speed, HOIS, HOIS plus LE. Still more needs, these are a partial capture of terms, partial, more partial, it's far from complete, yes? Here's Marmusi. 1, 2, green, blue, red, green, blue, red. Those are where actual structure are. So 2, yes. So 1 and 2 and 3 and 4 and 5 and 6 belong together. Okay? 1 is where the water speed image gives you. Yes? This is water speed image. Okay? Mislocated. In other words, the green, blue, red are actual where structure is. 2, 4, yes, and 6. 2, 4, and 6. And the water speed image is in each case too shallow. 1, 3, 5. And then when Professor Fang Lu puts it into his HOIS, they coincide. No information. Okay, so, but here's, first, let's talk about the caveats here. What's going on here is, as he moves into this rapid lateral varying area, the number of terms in HOIS is not sufficient, okay? It needs more terms. So you're going to see, you see this? Means common image gather not flat. You haven't, it's not at the right depth. Anywhere it's flat, you are at the right depth, okay? All the way to the left. When you're in the middle of that high complexity, needs more lateral exclusive terms. The big catch here is, this is for velocity only changing Earth. Velocity only changing. So we have a request. We're soliciting data. If you have a data set which is of a vintage where the sediments are consolidated, yes, older sediments, where the major reflectors are velocity only, we'd like to work with you to test this algorithm, yes? If you have major changes or velocity and density, we're not ready for that, okay? It's going to take more work. But if the major generators are velocity, and I'm told that that can occur, then we're interested in testing that. The Kristen data showed a viability. Here's what do you mean by viability? This image became flat, shifted and became flat. Okay. This was joint with Schlumberger and Statoil published this data. It was ExxonMobil was one of the owners of the data. They approved this results. Okay, so this is what happened there. So let me just show you one last thing. Q, Inin and Lira, myself work Q compensation without Q. There's a subseries. This data on top has suffered absorption and dispersion. It goes through a subseries as though it never had experienced. In other words, it was modeled with Q and without Q. Yes? So there were some issues that Inin and Lira had that we're visiting with them because we believe that the same issues that Professor Fang Lu addressed successfully for ISS depth imaging will occur here and will be addressable. We're looking for this to be a deliverable. Q compensation without knowing or needing Q. That's a game changer. Okay? Okay, so that's what this new opportunity is saying is the following. In addition to sponsorship, or separate from sponsorship, we're offering the following. If your company, oil or service company, has a play where one of the processing steps that we pioneer, develop, and deliver could show added value because you feel you have a challenge, that we're interested in working with you to model it, work with your team to model it, and to test and compare the difference between what you're doing today for some processing objective. So the particular objectives, we're looking at a deghosting for non-horizontal, we're looking at free surface and internal multiple elimination, and we're looking at Stolt C3 imaging. Several of those, the internal multiple elimination and the Stolt C3, are not available now. We have not distributed those to sponsors. So the only place you can find them is here. So let me say a word about that kind of activity. That activity would involve support for postdocs or research scientists, not students, and there would be a separate relationship beyond sponsorship. If you're a non-sponsor viewing this video and you have an interest in having a project together where we model and compare a data that you have and are suffering some issue that you feel we could add value, then first you would pay more for that service, and the second is you will never get the code. You'll get the result. Only sponsors get the code that come from MOSRP. But we welcome all ways to work with oil and some service companies, sponsors and non-sponsors alike, to help address outstanding problems. We very much appreciate all your encouragement and support, and we're coming close to the winter holidays. I want to wish everyone a good winter holiday and a happy, healthy, and prosperous new year. Thank you. Thanks.